Ever wondered why design modeling is crucial in object-oriented analysis and design, also known as OOAD? Well, let's dive right in. Design modeling in OOAD is akin to creating an intricate blueprint for a complex architectural project. It's a detailed visual representation of a system's architecture and its components. This process builds on the foundational work of domain and use case modeling, providing a comprehensive blueprint for software development. Now, you might be asking, why is this important? Well, design modeling serves as a vital bridge, one that connects high-level requirements to the nitty-gritty of low-level implementation. It helps us translate abstract requirements into tangible structures that developers can actually implement. So, in essence, design modeling is a translator, a guide, and a roadmap, all rolled into one. By now, you should have a basic understanding of what design modeling is and why it's a critical part of OOAD. Now let's delve deeper into the first key component of design modeling: class modeling. Class modeling is an indispensable part of design modeling in object-oriented analysis and design. It serves as the cornerstone of object-oriented design, providing a comprehensive blueprint of the system's static structure. This structure includes classes, attributes, methods, and relationships, all of which are critical building blocks of the system. A primary tool for class modeling is the class diagram. This visual representation defines classes along with their attributes and methods. It also outlines relationships among classes. These relationships could be associations, aggregations, or compositions. Class diagrams are instrumental in defining object-oriented principles such as encapsulation, inheritance, and polymorphism. They provide a clear, unambiguous picture of the system's structure, which can be easily understood by both developers and stakeholders. Next, we have component diagrams. These diagrams focus on the higher-level software components and their interdependencies. They are particularly useful in large-scale systems, where they highlight modularization and the organization of code. Component diagrams help us visualize the overall system architecture and understand how different components interact with each other. Finally, we come to package diagrams. These diagrams are useful for grouping related classes into packages. They establish dependencies among these groups, which can guide developers in organizing code and managing complexity. Package diagrams help maintain the system's modularity, which is essential for scalability and maintainability. So why is class modeling significant? Well, it simplifies the system's complexity by breaking it down into manageable pieces. It provides a clear roadmap for developers, guiding them on how to implement the system based on its static structure. It also facilitates communication among team members and stakeholders, ensuring everyone has a shared understanding of the system. Moreover, it aids in detecting potential issues early in the development cycle, saving time and resources. Class modeling, in essence, provides a detailed view of the system's static structure. This view is foundational to object-oriented design and serves as a stepping stone towards the system's dynamic behavior, which we'll explore in the next segment. Interaction modeling. After class modeling, we move on to interaction modeling. Now, this is where we start to really see the system come to life. Interaction modeling is about understanding how objects in the system communicate with each other. It's about identifying the order and nature of message exchanges between these objects. In the world of object-oriented analysis and design, we have three primary tools for interaction modeling. First, we have sequence diagrams. These are time-ordered diagrams that showcase the sequence of interactions happening between objects. They help us visualize the order of operations and how different parts of our system communicate over time. Next, we have communication diagrams. These are more spatial, showcasing the relationships between objects. Communication diagrams show us how objects relate to one another and how messages flow between them. It's a bit like looking at a map of a city, where the objects are landmarks and the messages are routes connecting them. Finally, we have activity diagrams. These diagrams are all about workflows. They help us map out the sequence of operations within a system or a use case. Imagine it like a flowchart illustrating the steps of a process or the flow of control in a system. Each of these diagrams serves a unique purpose, but together they provide a comprehensive view of interactions within our system. They allow us to understand not just what the objects in our system are, but how they communicate and collaborate to perform tasks. Interaction modeling is a bit like choreographing a dance. It's about understanding how each dancer, or in our case object, moves and interacts with the others. It's about the timing, the order, the flow. It's about ensuring that each object knows when to step in and when to step back, ensuring the whole system works in harmony. By doing this, we can design systems that are efficient, reliable, and easy to understand. We can identify potential bottlenecks and areas for improvement. We can ensure that our system does what it's supposed to do in the best way possible. Interaction modeling, therefore, helps us understand the order and nature of message exchanges between objects. Next on the list is behavioral modeling. Diving into the world of behavioral modeling, let's think of it as the method of outlining how a system or an object within that system interacts over time. It's the part of the design modeling process that helps us understand the dynamic behavior of a system, giving us a clear picture of the system's operations. So what do we use for behavioral modeling? Well, we have a few different types of diagrams at our disposal. Let's start with state diagrams. These diagrams are like snapshots that capture the various states of an object or a system, and the transitions that occur based on different events or conditions. They're particularly useful in situations where an object's behavior is heavily influenced by its state. Next, we have activity diagrams. Now, you might remember these from our discussion on interaction modeling, but these diagrams are versatile. They can also be used in behavioral modeling to describe the flow of activities within a system. This makes them incredibly valuable for modeling business processes and logic. Last but not least, we have use case diagrams. Now, these are more commonly seen during the analysis phase, but they do have a role to play in design too. Use case diagrams are excellent at illustrating the interactions between the different actors and the system. They give us a high-level view of who does what in the system, without going into the nitty-gritty of how it's done. Now you might be wondering, why go through all the trouble of behavioral modeling? Well, it provides a clear picture of the system's behavior and operations. It allows us to understand how the system responds to inputs, how it changes over time, and how different parts of the system interact with each other. It's like having a bird's eye view of a bustling city, watching how the different parts move and interact in real time. Behavioral modeling provides a clear picture of the system's behavior and operations. Finally, we have deployment modeling. This is the final piece of the design modeling puzzle in object-oriented analysis and design. Deployment modeling involves creating a visual representation of how software components are distributed and interact on hardware nodes. This might sound a bit complex, but it's essentially about understanding where the software lives and how it communicates within the technical infrastructure. Now, you might be wondering why this is important. Well, imagine building a house without a plan for where the plumbing or electrical systems will be installed. You'd end up with a beautiful house, but turning on a light or flushing a toilet might be a problem. In the same way, deployment modeling helps us avoid such issues in software development. The key tool here is the deployment diagram. These diagrams are like the blueprints of your software's physical architecture. They illustrate the configuration of runtime processing nodes and the components that live on them. They also depict the network connections between these nodes, showing how the components interact and communicate with each other. Deployment diagrams don't just help us understand the current state of a system's physical architecture, they also allow us to plan for future changes and expansions. They provide a clear view of the system's scalability and help us identify potential bottlenecks or points of failure. Deployment modeling, therefore, is essential in planning the physical architecture and deployment of software systems. Now that we've covered the components of design modeling, let's talk about its benefits and some best practices. Design modeling clarifies the system structure, providing a visual representation of the architecture. It's like a map for your software, making it easier to understand and communicate about your system. But it doesn't stop at clarification. Design modeling also facilitates design review. By creating a tangible model, stakeholders can review and ensure alignment with requirements. It's an opportunity to identify potential issues early, saving you time and resources down the line. And let's not forget about implementation. Developers use design models as blueprints for coding. This reduces ambiguity and promotes consistency across the development team. Even after deployment, design modeling continues to provide value. It supports testing and maintenance by providing a clear design structure. This aids in planning test cases and maintaining the software over time. So, what are some best practices to consider? Firstly, keep it simple. Design models should be comprehensive but not overly complex. They need to communicate, not confuse. Secondly, ensure consistency. Your design models should align with requirements and reflect the system accurately. Lastly, but importantly, keep your models updated. As your system evolves, so should your models. Remember, the goal of design modeling in OOAD is to create a clear, understandable, and consistent representation of your system.